All right, thank you, Timo. Let's see. So thanks, Timo, for the introduction, for explaining the motivation of Excalibur. It sounds really interesting and exciting project. And thank you to you and Simon for organizing the workshop and for inviting me to participate in it. So let me just begin. Emory University is in Atlanta, Georgia, which is in the southeast part of the United States. I guess Atlanta is known for many things. And one is Emory University. Actually, Emory is probably the biggest employer in the Atlanta metropolitan area, with the university and the healthcare that goes on here. Its medical school is very well known for a variety of different things. One is developing an AIDS drug that is probably the most used AIDS drug in the world now. And it's also been heavily involved in recent COVID studies, especially in developing the Moderna vaccine. I want to mention this is our group in scientific computing at Emory. So I'm up in this upper left corner. This is Lars Rothoto. You may know him. He's doing a lot of work in inverse problems and machine learning these days. Talia Mayo is another professor in our department. She does data assimilation, modeling storm surges from hurricanes. Yunja Shi, he's numerical linear algebra and doing a lot of applications in machine learning these days. Bree Ettinger is doing things like spline data fitting, and Alessandro Veneziani is doing a lot of work in modeling blood flow in cardiac modeling. So we have a lot of collaborations actually with the School of Medicine. So let me just come to my talk now. Right, so I wanted to say something about some work that we've been doing recently on Kriloff subspace methods, and in particular, the more recent work on low-rank regularization. And that work is a joint with one of my PhD students, Chung Meng, and Sylvia Gazzola. I think many of you know Sylvia, who's at the University of Bath. And I've had a long collaboration with Sylvia over the years, and she's a fabulous person to work with, and I really enjoy my collaboration with her. All right, so I want to talk about basically linear inverse problems, and in particular, computing solutions that have what we might call a low rank structure. And by low rank, I mean a low tensor rank in some sense. So, this denotes sort of, if you like, matrix or vector Kronecker product or tensor product. And the idea here is to find solutions that have a short number of terms here in the rank. Now, the word rank is related to matrix rank, because if you reshape this this vector, if you like, into an array, then it looks like a low rank matrix. And you can extend this idea to three-dimensional cubes, if you like, and you talk about low rank tensor decompositions. Now, to get here, to describe our algorithms, actually, since it's a workshop, I wanted to take some time to run through the steps on how we got there. And some of it's going to be review. So I'll talk a little bit about basics of Kriloff methods for inverse problems. Talk a little bit about hybrid methods that have been around for a number of years. And then from that, take us through the ideas that we sort of, how we sort of got to this idea of doing low rank approximations. So I'll talk a little bit about sparse reconstruction and non-negative reconstructions in the context of Kriloff subspace methods. So by Kriloff subspace methods, I mean things like conjugate gradient type methods. All right, so we all know this is a workshop in inverse problems. So if you're working on inverse problems, you know that if you run an iterative scheme on an inverse problem, like conjugate gradient type method, and these are just different types of conjugate gradient type methods, LSQR, GMRAS, and so forth, that if you truncate the iterations early, and that is, don't drive the residual to zero, the solution tends to mimic what might look like a truncated SVD regularized type solution. Of course, that means you need to know when to stop the iteration. And if you're not sure about when to do that, you might prefer to add some variational regularization to the problem and try to do minimization where you drive the residual small, in some sense balanced with driving your regularized operator to zero or to small as well. And of course, there are many choices for your regularization. And of course, there's always the question that comes up when you talk about these things: how are you choosing your regularization parameters? Right. So there isn't, of course, those of you who are experts in inverse problems know that there's not one method that fits all problems and all data. And so you don't have a simple flow chart to choose by. And so, so my work has been, and with Sylvia, and I'm going to talk some work about with Sylvia and Per Christian Hansen, is not necessarily to advocate for one regularization method over another, but instead to develop software tools that people could use to easily solve a variety of different problems. All right, so I'm going to talk in this talk focus on Krylov subspace methods combined with SVD. So we'll call those in some sense hybrid type methods. All right, so let me begin with just the framework for Krylov subspace methods. So this is again like conjugate gradient type methods. The idea here is in Krylov subspace methods is you generate a Krylov subspace and a basis for that Krylov subspace. So you can think about the vectors in a matrix V and a matrix U as being basis vectors, if you like. And you relate a large scale matrix, which models your forward problem into, transforms it, these basis vectors transforms it into what I might call a tiny matrix. And the size of that matrix depends on the number of basis vectors that you have. And so when you do this, you can then sort of project the large scale problem. So matrix A again is a large matrix down to the tiny problem, solve over for this tiny problem, and then project back. That's the basic idea of all sort of Krylov subspace methods. So each iteration, you solve a tiny problem, project back. And so instead of solving your sort of least squares problem, if you like, for all vectors, you're only solving at each iteration over a set of a subspace. Now the subspace grows at each iteration, so then you would think, well, as the subspace grows, I should of course get better and better approximations. And the nice thing about Krylov subspace methods is that if you in the early iterations, these solutions at each iteration mimic a truncated SVD solution. So the idea here is that in early iterations, this matrix T starts to pick off the large singular values and information about the corresponding singular vectors in the early iterations. So if you stop early, you get a solution that involves the large singular values and singular vectors. So it mimics a TSVD type solution. And of course, you have to stop the iteration when the solution is good enough, whatever that means for your particular application. And again, this is not recent, this is not new. There's a lot of nice books where you can find more information about this. There's a nice early book by Martin Hanke. And then, of course, there's books by Per Christian Hansen and this book by Engel, Hanke, and Neubauer. I also want to mention this survey paper that's a little bit more recent by Sylvia and her collaborators from Padova. And so if you're interested, I would highly recommend this paper here. So this paper in Etna. So as I said, Sylvia and Per Christian Hansen and I decided that what we want to do is not advocate for one regularization method over another, but to try to develop schemes for a variety of different problems, and then to try to put them together into a toolbox that people could use for solving. So it's a Matlab toolbox that we call IR tools, so IR for iterative regularization. And you can get it via GitHub if you like. And so, the idea was to make these codes for these Krylov subspace methods sort of easy to use. And so we can, since it's a workshop, if you don't mind, I'm going to run some, well, actually, if you do mind, it doesn't matter. I have control over the screen right now. So I'm going to run a couple of Matlab illustrations just to show you basically how easy it is. it would be nice for inverse problems if we had a backslash operator. And of course, we don't have a backslash operator. But we wanted to develop iterative methods in such a way that if you don't know much about your problem, all you know is the matrix or an operator that can do matrix vector multiplies. So you don't need to know A explicitly, you just need to know how to do matvec mults and your data. Can you get a solution out? And so I wanted to show you some Matlab illustrations for this. And so let me show some examples. I'm just going to create, this is a very simple test problem in our toolbox. In our toolbox, we've provided not only methods, but we wanted to have problems. So PR for a problem. And this is a seismic, really simple seismic tomography illustration. You can add noise to your data very easily. So you don't have to have any inputs to our problems, test problems. You can change inputs if you want to, but if you just want to try a quick test problem, just load it basically. And it will return whatever your matrix operator is. It could be a sparse matrix, it could be something else, a function handle, depending on the test problem. You have true data, true solution, and some information about the solution. And of course, we always should add some noise to the data. And this is what the data looks like. Okay, so this is my measured data in this panel, and this is the true solution that I'm after. And so I just run my CG solution on it. And when I do, okay, I didn't give it any information. I didn't ask it to do any regularization or anything. So it has to default to a certain number of iterations. Now I can change that default easily if I want to, but if it runs the default number of iterations, it gives me a solution, but you all are experts in inverse problems. You know that it looks like I've overfitted the data. So nice thing about the toolbox is to try to play around and see what's going on here. So I know what the true solution is in this particular test problem, so I can give it to my method by just putting it in as an extra option. And if I do that, I can then look at what's going on at each iteration. So for example, I could plot the norm of the error at each iteration between that and the truth, and see what it looks like. And if I do, I get this plot here. So here's my relative error here, and of course my iteration. And you see the sort of classic semi-convergence behavior going on, where you see, okay, yeah, for sure you overfitted by doing 100 iterations. You should have stopped down there somewhere. Of course, it's a bit unsatisfying because I don't have a true solution in most applications. And so, of course, you should do other things, right? So, and so the typical thing is to think about, how are you going to either regularize or choose the stopping criteria. And the easiest stopping criteria is, of course, the discrepancy principle. So if I know something about the norm of my noise, I actually can put it in as an option into to my method and see how well it works. Okay, so we set the noise level to be whatever value we think it is, and then we input it into the code. So let me run that example just to show you that it works. So I'm going to put in the noise level and run the same thing, and it stops quite early actually, and in fact gives me a pretty decent solution. And I put a little red dot here to say where it stopped there. Now, of course, you could play with changing the noise level and various fudge factors that are involved with discrepancy principle, and those can all be changed through this options if you know what you're doing. But if you don't, you just play around a little bit. Of course, you could say, well, I don't know the noise level. And you say, well, but I know a regularization parameter that I would like to use, and I want to do something simple like ticking off, and that's easy to do as well. So I won't do an illustration of that, but the idea is that you can just easily tell the code what the regularization parameters you think it is, 0.1483, I don't know what it is. Make up a number and put it in, and then run the code and see what solution you get out. All right, so these are easy sort of test problems, but I wanted to illustrate that the main takeaway here is that these codes are quite easy to use. And so if you have students that you're interested in getting involved in these things, it's pretty easy to get them going on these test problems. Set up a test problem, run it, and see what happens. All right, So of course, if I don't know noise level and I don't know what a good initial regularization parameter is, what can you do? And that's where we come to the sort of hybrid type Krylov methods. So again, remember at each iteration of a Krylov subspace method, you're creating a set of basis vectors in this V matrix, if you like. You solve a tiny projected problem and then you project back each time. And so when I solve this, this tiny projected problem, as I said, this matrix here starts to pick up components corresponding to the largest singular values. So as the iteration goes on, I start to pick up smaller and smaller singular values. And so what you might do to prevent the semi-convergence behavior from happening is to regularize the projected problem. And the advantage of doing that, rather than regularizing the original large scale problem, is that this is a tiny problem here. And so you can do a lot of things with this tiny problem to choose, say, regularization parameters that you couldn't do on the large scale problem. So for example, this T matrix is small enough, I can do an SVD of it, and I can do SVD analysis and so forth to help me determine what might be a good approximation for a regularization parameter. And so that's basically what we do, is we use things like generalized cross-validation or discrepancy principle to help us choose the regularization parameter at each iteration. Now that means the regularization parameter is changing at each iteration, but with a simple method like Tikhonov, this actually will converge to the Tikhonov solution if these regularization parameters are chosen in the right way. You can also compute information to help you figure out a good stopping criteria as well. And so these, again, are not new methods. The earliest work I know of these sorts of hybrid methods was by O'Leary and Simmons back in '81. And Aki Bjork did some work in the late 1980s and early 1990s as well. Martin Hanke has a nice paper in BIT on these methods. And our work is based on an implementation that I worked on with Diane O'Leary and Julian Chung when she was a PhD student with me. We call this method IR hybrid LSQR. It's based off this Golub-Kahan bidiagonalization under which LSQR is based on, except that we enforce the regularization at each iteration. Right, so again, the underlying Krylov subspace we use to find the regularization parameter, or at least an estimate of the regularization parameter, and use some information to help determine a stopping criteria. And just to show you it works, right? So the nice thing about these hybrid methods is that I don't need to give additional information about the noise unless I have it, or I don't need to give a regularization parameter unless I know something good about it. If I don't know anything, then I can just try to run this and see what happens. And so let me just come back to my example here, and I'm going to do basically the same example as I did here, except this time I'm going to run the LSQR code. And again, it's trying to determine a regularization parameter each iteration, and then it figures out a place to stop. And so if I plot the solution, it looks just as good as what I did before with CGLS, knowing the noise or guessing a regularization parameter. Here, I don't have to know very much about it. Now, as I said, each iteration of this method tries to estimate a regularization parameter as it goes. Now, in the beginning, the early iterations, you don't have a lot of information, so it's hard to know what to do. So typically, we don't start looking for regularization parameters until we've run a few iterations at first. So let me plot up in this upper left what the regularization parameters look like at each iteration. So in the beginning, as I said, we don't regularize at all. At a certain point, we say, okay, let's start to regularize. Now, I can change that in the code if I want to, but I don't have to. So at some point, we start to estimate a regularization parameter. Now, again, this is early iterations. I don't have a lot of information about my singular values and corresponding singular vectors in the beginning. And so it takes a few iterations for it to figure out what's going on here. So, and as it does, the regularization parameters tend to level off, and then it recognizes the stopping criteria and gives you a nice solution in this particular case. Now, I will never claim, especially to any inverse problems crowd, that this will work as a foolproof method for all inverse problems, because that's not true. It can't be possible. But it does work well on quite a lot of problems. And I'll show some more examples in a minute. All right, so that's the basic idea of these hybrid methods. There are, again, you can, if you want to, if you know a little bit more about your problem, you can input this in terms of additional options if you like, but you don't have to. I want to mention that there are also methods based on something called the Arnoldi scheme. So rather than Golub-Kaham bidiagonalization, Arnoldi is another Krylov type subspace method that is sort of the basis of GMRes. And the nice thing about these Arnoldi-based methods is that you don't need a transpose multiply for your matrix. And so, so that can be an advantage in certain applications. I should mention that this is Sylvia pioneered a lot of, so some of the work was first proposed by Lothar Reichel and his collaborators, but Sylvia developed a lot of this work during her PhD studies, and there's a lot of excellent work that she's done corresponding to this. I also want to mention that, you know, so if you have a sort of Tikhonov regularization problem with a not identity matrix here, if this matrix L is invertible, you can, of course, transform to standard form, and then everything else falls through after that. If this matrix is, say, underdetermined, like a derivative operator, then you have to do a little bit more work. And there's some work by Misha Kilmer, Per Christian, and Milena Espinol on how to do that. All right, so now I want to come to, so as I said, I want to, since the workshop, take you through the steps on how we get to eventually to this idea of low rank approximations. So the next step in the process is to say, okay, well, let me go past the idea of just a 2-norm regularization to something as simple as an L1 regularization. And I know there's lots of schemes to solve these problems, but we were interested in saying, okay, how could you do this within a Krylov subspace framework? And this is actually the first project that I worked on with Sylvia when she visited me several years ago. And so the idea was to develop a first look at an idea of iteratively reweighted norm approach. Again, this is not a new idea. And so the basic idea is the following, is that, well, you know, these mix of quadratic and not quadratic makes the problem a bit more challenging. So if I had 2 quadratic terms, of course, then it's just like Tikhonov regularization, easy to solve. And so the iteratively reweighted norm approach says, okay, let's replace this L1 norm with a 2 norm, a weighted 2 norm such that I choose the weights so that this weighted 2 norm approximates the 1 norm. And of course, the easiest choice, of course, is if I know the true X solution, that weight matrix will be a diagonal. And on the diagonal would be the components of that solution X, square root of 1 over square root of that, those components. So something like this here. Of course, I don't know the true solution, and so the idea is to iteratively reweight. So take an initial guess, X0, take a weight matrix based on that, put it in here, replace, and iteratively keep solving. And each solution, you get a new weight matrix, you put it in, you solve. Now, the problem with this kind of approach, of course, is that it's somewhat expensive, right? You have to keep solving this large-scale problem over and over again until you're satisfied with your solution. And so, so what Sylvia and I noticed is that, well, this looks, you know, so much like Tikhonov regularization. Why not think about it as sort of transforming to standard form? The idea is kind of simple in some sense, now that you think about it. Transform to standard form, and then look at it as like a preconditioned least squares problem. Okay, so now it looks like a standard Tikhonov regularization problem, except that I have this different matrix here. And it looks like sort of the classic preconditioning, except that the preconditioner changes at each problem. And so if you want to say solve a preconditioned least squares problem with a Kriloff subspace method, and the preconditioner depends on the iteration, then you need to use the right Krylov subspace method. And those right Krylov subspace methods are called flexible Krylov methods. And they've been around, again, for a number of years, but they hadn't been applied to this kind of problem until Sylvia and I looked at it. And so the idea was quite nice, and so we got, I think, quite a nice code out of it. The idea is to think about it as an sort of iteration-independent preconditioner. I should say that Sylvia and Julian Chung extended this work to other types of methods, and they have a nice paper on that in SISC. And then more recently, Sylvia and one of her former PhD students, Milena Sabate-Landman, have a nice paper that should be coming out in SISC soon. All right, so again, we implemented this in our toolbox. We call it an L1 minimization. And again, you can change the options if you want to change things around. Actually, I'm not going to show an example of this. We actually are going to sort of modify this. Right now, it's based on a GMRes. So it's sort of restricted to the sense that I need a square matrix in here to be able to think about using GMRes type methods here. The method works well, but we're going to sort of make it more applicable to other problems as well. All right, so let me just jump quickly to another type of problem that Sylvia worked on, and that was to try to think about, can you extend these ideas of weighted variable preconditioning to get solutions with just simple non-negativity constraint on it. And so the idea here is to think about the KKT conditions, and then think about this like a fixed point iteration, of course. And when you write it down like that, then you have something that looks like, again, like a sort of a preconditioned normal equations, if you like. And the preconditioner here, again, depends on the solution at each iteration. And so it takes a bit of work to explain this method, so I'm not going to go through the details, and I'll refer to Sylvia's paper on that. But the idea is to implement this within a Krylov subspace method. I believe she also has some sort of like bounded line search on this to make sure that the solutions stay non-negative. It's a very nice paper, and the scheme is quite nice. We implemented it in this method here, and again, once again, the idea here is to develop a set of software tools that people could use without needing to know very much about what's going on. So let me just quickly illustrate this one. Just to show you that it works with this simple test problem that I've been working on. So again, let me just run the LSQR code again, just so to remind you, it stops after a certain number of iterations and gives me a solution that looks like that. And of course, enforcing a non-negativity constraint adds a little bit more regularization to the problem. It takes a bit more work per iteration, so you can see each iteration maybe is a bit more costly. And I think in this particular case, it runs to a maximum number of iterations. But the nice thing about, of course, adding a non-negativity constraint on it is that, again, it adds a bit more regularization to the problem. And so it helps to sort of stabilize what happens at each iteration. By the way, I am running this on my MacBook Pro right now. It's an old MacBook Pro, and I haven't pre-computed anything. So that's what the solution looks like. The constraint actually adds a nice little regularization. You might look in some of these regions and say you overfit. So why not do something else? And again, you can just to illustrate, if you know something about the noise level, you can, of course, add that to your problem. And if you do, typically, you might get a solution that maybe looks less overfit. Of course, again, if you don't know the noise level, you can let the code figure out what to do on its own. Now you may say, okay, great. These are really cheap test problems. You're probably committing inverse crimes and all sorts of things. So let me just, well, let me do this. I'm going to do a cheese example. And maybe you know what this cheese example is. It comes from the FIPS data set. Let me come over here for a second so you can, just to show you. It comes, of course, from the Finnish Inverse Problem Society. They have a bunch of nice data sets that they've kindly put publicly available for people to download. And I'm using this, this cheese data set here just to illustrate. Now, this first example is a full CT in some sense problem. It takes data at 180 different projections. And so this is what the projection data looks like. And so I'll just take whatever their data was, rewrap it into a vector so that I can use it in our codes in sort of the usual way. So that all you need to know is the matrix A that they gave us and the data that they gave us, and we get a reconstruction. And again, if you want to use sort of a constrained kind of solution, you can do the same sort of thing. And again, just give it matrix A and vector B and see what kind of solution comes out. And yeah, sorry if it takes a couple of seconds for it to finish. Yeah, so so we get something that looks like that. And you say, oh, well, I still don't like your solution. My methods are better. That's fine. In fact, I'd be glad for you to compare and show us that you can do a lot better. If you want to use another one of their data sets, this one's a more limited angle tomography problem, so 15 angles. So here's the projection data. And again, if I run our hybrid LSQR method, we get a solution that looks like that. Probably not so unusual because of the limited angle. And again, if you add a constraint on it, it might help improve things as well. All right, so so this is sort of the sort of what we have so far in our toolbox. I should say that we have actually a lot other codes, not necessarily these Krylov subspace methods, but methods that have been developed by other people. But we wanted to include them as well because we think they're great methods. And again, as I mentioned in the beginning, we're not trying to say that our methods are going to beat out every other method in all problems, but they can work quite well for many different kinds of problems. So we included a whole bunch of methods in the toolbox. All right, so let me come to the low rank solution part again. As I said, I wanted to take you through the steps because the details, the mathematical details of this get a little hairy. So the idea is, again, we want to compute a solution that has, in some sense, low Kronecker rank, if you like. And again, it's related to matrix rank if we reshape things into an array, or a tensor rank if we reshape it into a 3D cube. And the idea here is, of course, if I have an image, you know, I can think about the rank of this image array, think about it as like a matrix. And if you truncate its singular values, of course, and the image didn't change at all, right? So there's the full image. If I approximate it by a low rank approximation, it looks exactly the same. And if I even go lower, it still looks pretty darn good. So these low rank approximations do give me a good representation of the solution. Right, so we were motivated actually by some work in the stochastic PDE literature by a variety of people where they were trying to use Kriloff subspace methods to compute low rank tensor approximations for solutions. And we wanted to say, well, so could you do that? It makes sense in our inverse problems to try to do this in terms of a regularization type approach. And so, so the idea here that we borrowed from them goes something like this. So you compute, again, a Krylov subspace. So you have these set of Krylov vectors that you're using, and you have this sort of projection problem, right? You find your projected vector y, and then you project back to give your solution to the large scale problem at each iteration. And the idea here is if X has low tensor rank, then you would expect this, of course, VM to have low tensor rank. And so how do you ensure that at each iteration? And so you have to sort of look at what the mathematical relationships are in a Kriloff subspace method, and you get something that looks something like this. So you have to think about these vectors that are computed at each iteration. And the idea here is that if I start off with something and say, I think X is a low tensor rank, so I start with an initial guess that's a low tensor rank, and I start doing some work. The problem is you start to lose that low tensor rank. Any matrix vector, if I take a vector that has low tensor rank and I multiply it by a matrix, most likely that rank is going to increase, and it could increase quite a lot. So what they did in these works is to say, well, let's truncate. We know we expect it should have low tensor rank, so let's truncate things as we go. Right. So yeah. So as I said, matrix vector products and sums increase the rank for sure. And so what they did is they decided, well, let's truncate at each step. So it involves some SVDs, but they're SVDs of reshaped vectors. Okay, so they're not necessarily expensive SVDs, but you do have to do something there. And you also have to decide what your truncation level is going to be. All right, so that's the idea. Again, even if I truncate this stuff to make it low tensor rank, the matrix V times the low tensor rank is likely to increase the rank as well. So what you do is you truncate, and then you say, okay, after a certain number of iterations, I'm going to truncate my solution because I expect it to have low rank, and then restart. Okay, well, I don't know. It sounds interesting, and so we wanted to try it just to see how it would work. Now, in our case, so these methods were based basically on GMRes type methods. And so we want to extend it to something that would be more flexible. And so we did it in terms of a Golub-Kahan bidiagonalization approach so that the matrix doesn't need to be square. It can be any shape that you want. And so for this, we needed some recent work by Sylvia and Julianne Chung. And this is called the flexible Golub-Kahan bidiagonalization. Not important that much about what it creates. Basically, again, it projects down to a tiny problem. You solve the projected problem, and then you project back. Okay, so that's the basic idea. And we implemented this idea in terms of using the truncation approach. So restrict the number of Kronecker products that we expect to have in the columns of the basis vectors that we create, and also in the approximate solution. All right, so it worked, kind of worked, but it was a bit unsatisfying to us because there was this idea here of say you had to choose this truncation, you had to make this truncation operator, and you had to decide ahead of time what your truncation level was going to be. How many terms did you want to truncate? And we thought, well, what if you don't know that? What would you do? So we decided to go to the idea of doing a nuclear norm type regularization instead. And so the idea here is to reshape your vector into a matrix, and then regularize, in some sense, the number of non-zero singular values. So we'll use a sum of singular values here. And so if we can sort of regularize by that, it sort of enforces implicitly a low rank approximation on your solution. So that was the idea. And again, we recognize this looks like a lot like what we did for the L1 regularization, only we're using a different type of regularization on it. It gets a bit more complicated. We wanted to also think about whether we could sort of get more singular value sparsity of it. And so those ideas, of course, can be by changing the norm here, rather than say like a one norm, to use a sort of like P norm, if you like. And again, some of the work that motivated us to go to nuclear norm is again work that's been done previously. And so we were sort of motivated by that. We decided that we wanted to take this idea of iteratively reweighted norm again and adapt what we did for the L1 regularization to this kind of nuclear norm idea. The problem is that the weighting matrix gets a bit more complicated. And I know this looks like a mess. And in fact, I don't really want to spend too much time explaining it. I'm going to take my solution vector X, whatever I have at a certain iteration, reshape it into a matrix. Compute its SVD. So I have the SVD, the singular values of the solution vector and its corresponding singular vectors. That forms this weighting matrix. I'm not going to take you through the math on how I got there or how we got there, but just trust me that this is this sort of weighting matrix in here. And the idea here is quite similar to iteratively reweighted norm.
Sorry, James, 5 more minutes.
Okay, thank you, Timo. So you have this this weighting matrix here, and so you want to be able to solve this sort of weighted least squares problem at each iteration. So I have an iteration, compute a weight, and then update. Right. So I have this sort of inner outer iteration because I have to compute, update the weights, solve and do an iterative method to solve the large scale problem, and continue on. So the idea is kind of nice. You can transform to, if you like transform to standard form again. And again, these matrices, they look messy, but they're really not that messy to deal with in the code. And so now you have something that looks like a preconditioned sort of least squares problem, Tikhonov regularized least squares problem. And this weight here, this weighting matrix that you use at each iteration is helping to enforce, if you like, singular value sparsity in the solution, or low rank approximation in the solution. Right, so you have an iterative method that you update these weights and then solve. And again, you can think about it in terms of a flexible preconditioning kind of idea. And that's where we wanted to get to eventually, and that's what we did. And so you can use the ideas, all of the ideas that we did in the sort of hybrid type methods with flexible Krylov subspace methods to actually help you tune regularization parameters as you go and update the weights as you go. And the interesting thing about it is that in our paper, I won't explain it here, but we also noticed that the weights that we used in here, these weight matrices here, you can actually, there are actually different options for these weight matrices. I won't explain those here because it gets a bit complicated, but there are alternatives to those weight matrices. And so those are different, we did different experiments in the paper. Okay, since I'm running out of time, let me just show one quick example. I won't show any more Matlab, but just one quick example. So we did a problem where we had an image that was blurred and also some pixels missing. And so we ran our LSQR code on it and we got this solution here. It's okay, I guess. You can at least see that it's a house. We used the sort of basic idea of the low rank truncation idea. It did okay, maybe a little bit better. Again, that was not so satisfying to us, which is the reason why we went to this idea of doing the nuclear norm regularization, which seems to do quite a bit better in this particular example. Right, since I'm out of time, let me just quickly close. I think these Krylov subspace methods can be powerful approaches for these large scale inverse problems. Again, I'm not going to claim that they're the best methods for all problems, but they're nice. And I think that we've provided a nice set of tools for people to use. And so you're welcome to use them on your own test problems. I should say that we combine this with Jakob and Per Christian's work on tomography tools. So a lot of our tomography examples, like the seismic tomography one I used before, actually is taken from this package here. So they're sort of connected together, if you like. And so I'll just quit here. If you want to get the paper explaining the software and the code, you're welcome to it. So thank you very much.